So let me back up a minute. Let's pretend that this problem was this. Let's pretend that f of x was equal to x squared. And then I told you that g was an antiderivative. And then I told you that g of 5 was 7. Right? So what would, and matter of fact, let me make it even easier. Let's say I said g of 1 was 0. Let's do that. Okay? So, and you wanted to find g of 3. So what would you do? Find the antiderivative, right? You would find the antiderivative, which would be 1/3 x cubed plus c, right? That is solving a differential equation, isn't it? This will be a good lead-in for next week, right? Because really, isn't f a derivative in this case? Isn't that right? A differential equation is really an equation with derivatives in it. Well, technically, since g is the antiderivative, what's another name for f? G prime. So really, this equation is like saying g prime equals x squared. So it's really a differential equation, right, with an initial condition. So we do the antiderivative. Now, you can't do that on all differential equations. You can't do the antiderivative all the time, right? But one of the ways we can is we can do the antiderivative, put on the plus c, and now put in our initial condition, right? So we could plug in a 1, and we get 1/3. 1 cubed is just 1, right? Plus c equals 0. So c would be negative 1/3. So now what's the g function? 1/3 x cubed minus 1/3. And then what were we looking for? G of 3. So I would plug in a 3. 3 cubed is 27 times 1/3 is 9. 9 minus 1/3 is 8 2/3. Right? Isn't that how we would approach that problem? Okay, so now let's take that same approach up here. It's the same exact thing. I just did it with a simple one. So what do you want to do first? Take the antiderivative. Oh, antiderivative of x squared plus 4x to the 1/3 power. Can I just raise that up and divide and do a power rule on that? No way. No way, because of that stuff on the inside, right? I can't just do the antiderivative of that, right? Can I distribute that power through there? No, there is no, now, on your calculator, so everybody get your calculators out. Probably want to make sure you charge your calculators up tonight, because we're going to need them tomorrow, for sure, yes. That's fine, that's fine. Bring them tomorrow, though, okay? So, because we're not going to need them on today's homework, but tomorrow we're going to need calculators. So, okay? So, the calculator can do antiderivatives for you, right? So, here's how you do it. You go under where you get the integral symbol over there, in the template there by the 9, over by the 9, right? Get the integral symbol that doesn't have the numbers on it, right? The indefinite integral symbol. Get that one. And then type this in. Type in x squared plus 4x to the 1/3 power. And hit enter. And what do you get? It just spits it back out at you, doesn't it? Or does it rearrange it or something? Oh, it does. Oh. Oh. Well, that's not bad. I can't believe it does that. Well, no, but it still has the integral in it. Yeah, it still has an integral in it. So basically, it couldn't do it. A lot of times it'll just spit it back at you and it can't do it. There is no antiderivative of this. Okay? Well, that's a bummer because that means we can't do this technique we wanted to do right here. Right? Well, they did that on purpose. Right? They did that on purpose because remember, we've said not all functions have antiderivatives. Okay? There's another way we can do this. And the way we can do it is with an definite integral. We could do this. Okay, now let's think about this a minute. What does fundamental theorem part 2 tell us about this right here? Fundamental theorem part 2 says the answer to this is what? Big, just F or big F? Big F of B minus big F of A, right? Now, what's another name in this problem for big F? G of B, right? So let me erase a bunch. Let me get rid of this and start over here. So according to fundamental theorem part 2, and Jamie, I hear what you're saying, but let me just write this down. According to fundamental theorem part 2, wouldn't this be true? Right? Wouldn't this be true? Because G is an antiderivative of F, right? According to fundamental theorem part 2. Now the problem is we can't find G because there is no antiderivative. However, what would be good numbers to use for A and B in this problem? 1 and 5, right? Because you see those right here and here. So let's write that down. The integral from 1 to 5, and then let me put in my f, x squared plus 4x to the 1/3 dx is equal to g of 5 minus g of 1, right? Isn't this true? Okay, now, do we know g of 1? But that's what we want to find. So it's okay that we don't know that, right? That's what we're trying to find. Do we know g of 5? Can we find this? Can we find this?
Yeah.
How? Okay. Definite integral. What's one way to do a definite integral? The way we've done it most of the time. No. Without how do we do it when we don't get to use a calculator and on the gateway test? Fundamental theorem part 2. Find an antiderivative, plug in a 5, plug in a 1, right? But is that the only way we can do a definite integral? There are 3 ways to do a definite integral. One is a geometric shape, which this isn't. Another way is fundamental theorem part 2, where you need the antiderivative. What's the third way?
Yes.
Approximations, which is what we're talking about, right? Now, one of our great approximation techniques, matter of fact, it's going to become our all-time favorite approximation techniques, is what? Type it into our calculator. And let the calculator do the approximation technique. That is going to be the one we're going to love. Because our calculator can do that definite integral on the left side. If it can't do it exactly with the fundamental theorem, remember I've shown you some of that, where it'll give you an exact answer, and then sometimes it'll give you a decimal. When does it give you a decimal? When it's an approximation technique, when it can't find the exact answer. So, I'll ask again, can we find this? We're just going to type it into our calculator. And we know that that's 7, so here we go. So, I could rearrange this a little bit. I could add the g of 1 over to this side. And then I could subtract the integral from this side. So, g of 5 minus that integral. Now, you guys type that in your calculator. So, type in 7. What's g of 5? 7? So, type in 7 minus, and then do the integral, the definite integral, from 1 to 5 of that. And then hit enter. Right? So that's a really important lesson right there that we just learned in that problem that's going to be an ongoing thing. Is one way, this is kind of a differential equation in disguise, but one way when we want to do an antiderivative, we've got this function, we know something about its antiderivative, or we want its antiderivative, we want to find some values, we have one value, we want another value. One way to do it is do the antiderivative like we did earlier, do the antiderivative, find the C value, and then we can plug in and find any other values we want. But sometimes we can't do that. That's a limited way of doing it, because it only works when what? When you can do the antiderivative. But if you can't do the antiderivative, we can do it this way. Because remember, definite integral involves an antiderivative, but it also could involve an approximation technique as well. And our calculator could do this for us, okay? So we wouldn't probably have this question in a no calculator problem. All right, very good. Good question. Okay, what about exam 2, the other one, or exam, was that one we did, exam 2? Right? Any questions in that one? We can do one. We can do one.
34.
Whoever speaks up first. 34. This will be kind of ongoing to work in these two packets, okay? So we'll have an assignment tonight. It's not terribly long, so you should continue to work on multiple choice ones in here. Okay, 30. We'll have some work time on Thursday, although
Exam 2.
exam 2. Not sample, yeah, that one.
There's no 32.
Oh,
I said 34.
there's no 34 either. It goes to 28 and then it starts over. This is, are you in sample? You might be in the wrong packet. Exam 2. Okay, somebody got another one. 20 what? 21?
Okay, buddy. I can try.
I just got one thing.
20.
Yeah, I got B.
21. This one?
Yeah.
Why did we not do this one before? This should have been circled earlier. That's okay. We'll do it. Doesn't really relate to integrals, but that's okay because one of the things, matter of fact, we're going to start this on Thursday, is going back and reviewing some of this old stuff too. The normal. Now, we had a problem in one of the other packets where they actually said in the problem what a normal was. What's a normal line? It's a normal is what they're talking about. What's a normal line? It's related to a tangent line. It's perpendicular. So if this is a tangent line right here, then this would be the normal line. So it's all the same things you do to get a tangent line. You do this, except the slope will be what? Opposite reciprocal. Okay? So they give me the point, so I'll put a 1 there. F of 1, I'll put a 1 in here. And so that's 2 minus 3, that's negative 1. Into 1, that's negative 1. So that'll give me negative 1. So my point is 1, negative 1. And all I need here is a slope. How do I get the slope? Derivative, right? Get the slope by the derivative. That's good practice. How are we going to get that derivative? Quotient rule. Quotient rule is what? Derivative of the top, bottom left alone. Minus top left alone, derivative of the bottom, 2. All over, bottom squared. Right? And then all we got to do is plug in a 1. Right? Plug in a 1. So I can simplify it, but let's just plug in a 1, be just as easy. So 2 minus 3 is negative 1. Negative 1 minus 2 is negative 3. Plug in a 1 here. 2 minus 3 is negative 1. Squared is 1. So we get negative 3. But the reciprocal, opposite reciprocal of that would be 1/3. So our normal line. So we got the slope. We got the point. So we get y equals 1/3 x minus 1/3 minus 1. That'd be y equals 1/3 x minus 4/3. Probably multiply everything by 3 would be smart. 3y equals x minus 4. And I start looking at my answers up here. It looks like they're all in standard form with the x written first. So probably subtract my 3y over to here. X minus 3y. Add my 4 over to the other side. So it looks like x minus 3y equals 4. X minus 3y equals 4, like that. Okay, that's a good one to practice some of that stuff from before. So equation of a tangent line, we need a point and the slope. They gave us the point. We need the slope. The slope comes from derivative. We need a quotient rule to get the derivative. But in this case, they asked for the normal line, so when we get our slope, we just have to do the opposite reciprocal. Plug that in, and then, normally we would be okay to just be done right here. But since it's multiple choice, we got to match it up, so we got to do a little algebra. Okay? All right. Let's move along and get your notes out here today. So we'll come back to that, and we probably we'll see if we have a little time to do some of those tomorrow. But continue to work on a few of those problems anyway. Chapter 6 is a short chapter. Probably finish it by the end of next week, before spring break is the plan. Do a quiz on it next Friday. If you're going to be gone next Friday, be thinking ahead. You want to take that ahead of time. Obviously waiting till after spring break might be difficult to do. Okay. All right. So this is stuff you already have in your notes, right? This is a left, a right, a midpoint trapezoid. Now, what we're going to talk about in chapter 6 is we're going to just investigate a little deeper these approximation techniques. Left rectangles, right rectangles, midpoint rectangles, and trapezoids. Okay, we're going to talk a little more about this over-under approximation, and we're going to be using these approximations a little bit. And we're going to talk about how far off they are, and what we're going to do is we're going to end up figuring out how in the world does a calculator, that one we just did, that integral we just did, remember we said there's no antiderivative, how does it know how to get the exact answer? Well, if there is no exact answer, right, if there is no antiderivative, we can't get the exact answer. How does the calculator know that that answer it's giving us is 12 decimal places of accuracy, which it is? It's programmed to do that. How is that program done? How did the programmer write that to figure out that this is how accurate it is without knowing the exact answer? I mean, it's kind of like saying, well, I'm almost there, and you don't even know where you're going. How in the world do you know you're almost there? Right? I mean, that's what it's like. But we're gonna show in this chapter how it does that, how it knows, how much error, how much it's off. Right? That's what we're going to be investigating with this. Now tomorrow I'm going to send you a calculator program where you can do, like if I want you to do 20 midpoints or 50 midpoints, you can just type it in and it'll do that. Okay? But for today we're going to do a few by hand again. We're going to be writing out some, we're going to do 3 and 5 and small numbers of subdivisions. But we're going to talk about another way of writing them. We've already talked about the trapezoid a little bit. And that is, if I look at left rectangles, most of the time we deal with even widths, right? Equal widths. So instead of writing out height, width, height, width, height, width, which I wanted you to do, why? Why did I want you to write all that out? So you see the pattern, right? So you see the pattern. But now, okay, we've done that. We did our sigmas. We came up with all that. So now at this point, it's like if all we want to do is calculate them, let's don't write that out every time. Now you can. If you want to do 5 left rectangles or write out height, width, I don't care. That's fine. Go ahead. But what we could do is factor out the width. And if you're doing tables, you pretty much have to, right? Because tables a lot of the times have unequal widths, like we saw in that pattern. So then you pretty much have to write them out. But if we're doing equal widths, let's just factor the width out. Now, the width is b minus a divided by n, right? N is how many subdivisions, and a and b is your total width, right? So delta x is just b minus a over n. So I could factor out delta x, and I would end up having something that looks like this. So this you might write down in your notes, okay? So this would be just another version of left rectangle. So it would be b minus a, and I'll show you why we're going to do this. Why I want to write this, because we're going to do a little bit of some figuring of some of these things here. But go ahead and factor out the b minus a over n, the width, And all you're left with is the first height plus the next height plus the next height. And of course on lefts, we always start at the far left edge and we end up one short of the right edge, x sub n minus 1, right? Okay, and then what would be different on a right?
Start with a little.
Yeah, we wouldn't have this one, and we would go one farther. Okay, so there would be rights. Okay, so n right rectangles, b minus a over n, pulled out in front, that's just the width, the delta x, and then f of x1, f of x2, all the way to f of x of n, right? Not a big deal. We've seen that before. And midpoints, same thing, right? We just take the width out, b minus a over n, and then first midpoint height, second midpoint height, and then the last midpoint height. That's what the m stands for, is midpoint. Okay, now, what happened on trapezoids? Remember that? What did we factor out? The 1/2 and the width. So you'd have b minus a over n, and then you'd also have a 1/2 out there. So what would the bottom look like? 2n, right? And then what would be inside? What would be inside the brackets? Where would it start? F of x0, 2 of the next one, 2 of the next one, 2, remember that? Because the trapezoid, first trapezoid started here and then it had the right edge. Then the next trapezoid, that right edge of the first was the right edge, or the left edge of the second. So it ended up looking like this. So the trapezoid, b minus a over 2n, and then you end up with this. Now I think from here on out, this is a pretty good way to think about trapezoids. But again, if you were on the AP test, if you're on a multiple choice question or free response question, and they want you to do 6 trapezoids, and you feel comfortable just writing out all 6 trapezoids, do it. That's fine. You don't have to use this formula, okay? But it might be easier. So like that one on our last quiz where we had those 10 subdivisions, I thought it was easier to just say, okay, they're all one wide, so I'm just going to take 1 of this y value, 2 of this one, 2 of this one, 2 of this one, add them all up, multiply by 1/2 times the width. So that's it. Now, we've got a new one to learn here. Well, actually, before we do this new one, let's talk about this, another way to do trapezoids. Another way, let me see where I got this. Okay. Another way to do trapezoids. Think about this. If I took this one and added it to this one, right? If I took lefts and rights and added them together, think about what I would get. They both have a b minus a over n in front, so I would have that out in front. And if I added these together, look what I'd have. I'd have 1 of these, I'd have 1 of these, and I'd have 2 of all the rest. That's almost a trapezoid, isn't it? What's the only thing missing? The 2 on the bottom. So, wouldn't it be true that a trapezoid is just a left added to a right and then divided by 2? It really is. Now, it kind of makes sense that that's what you get, because if you think of a curve, and if you look at the left rectangle, it'd be that. If you look at a right rectangle, it would be that. And where would the trapezoid be? Right there? Doesn't it look like that would just be an average of those two? And that's exactly what it is. Matter of fact, some of you guys figured out the very first day. That very first day, we did that problem where, remember, we had those speeds, and we wanted to know how far we went in those 5 seconds. And if you did the left rectangles, you had 180. And if you did the right rectangles, you had 210. And a lot of you just did an average of those, and you had 195, which is right in between them, right? And that's what it is. So a trapezoid is just an average of the left and the right. From here on out, that's fine to use if you want. So if you've already done an L6 and an R6, and they want you to do a T6, then don't write out the T6. Just do L6 plus R6 and divide by 2. And that's perfectly fine. Now, if you haven't already done L6 and R6 and they want you to do a T6, then you got your choice. You can either write out the T6 or you can do L6 and do R6 and then average. Either way is fine. This is a perfectly valid way to do a trapezoid. Now, that's like a second formula we can use, okay, from here on out. Okay, here's the next one we have that we're going to do, and it is called Simpson's rule. Simpson's rule. So we'll use an S for that. Simpson's rule is another approximation technique. Now notice this one says S sub n, but the n has to be even. Simpson has to be an even number of subdivisions. So you have to do an S6 or an S8 or an S4. Okay, I will never ask you to do an odd. Okay, you can't. It's got to be even. Now notice what this one is. It's b minus a over 3n, so it's very similar to trapezoid. It uses the left edge like trapezoid does. Then it uses 4 of the next one, 2 of the next one, and it continues in that pattern. 4, 2, 4, 2, 4, 2, 4. It'll always end with 4s on the ends. And well, they're not actually the ends. The ends are x sub 0 and f of x sub n. But just inside of the ends, you'll have 4s. Because it'll always be even. So f of x sub 0, then 4, 2, 4, like so. And it'll always be in that pattern. Now, we're going to see in a minute why it comes out that way. Now, you're not going to have to ever come up with this, and you don't even have to write it down if you don't want to as we go through. Okay? But I want to show you where that comes from. Kind of like I just said, if you added these together, it's pretty easy to see that that adds up to double a trapezoid. So we just cut it in half. We average it, and there we got it. Okay? All right. So that's Simpson's rule. Now, Simpson's rule is more accurate. We talked about trapezoid is more accurate than lefts and rights, right? Because it's kind of an average. Lefts are probably going to be under, rights are going to be over, or vice versa. So a trapezoid is a nice mix of those two. It's an average. Okay? Well, midpoint's also better than left and right, right? Remember we talked about that? If you did a midpoint here, part of it would be over, part of it would be under. So midpoints were better than left and rights too. So it turns out left and rights are kind of like partners. They're kind of equally bad. Okay? Midpoints and trapezoids are kind of like partners. They're both kind of equally bad, but they're not as bad as these. They're better approximations. Right? If you're going to do 10 subdivisions, left and right aren't going to be very close. Midpoint trapezoid will be better. Okay? Well, it turns out Simpson's even better yet. Okay? Than any of them. More accurate. Now, why? Well, just like trapezoid is kind of a combination of these two, turns out that Simpson is a combination of these two, midpoint and trapezoid. It turns out, and we're going to investigate this a little bit in a minute, that if a trapezoid is under, a midpoint's over, and vice versa. So that's why I say midpoint and trapezoid are kind of like partners. Well, if one of these is under and the other one's over, it would seem like some sort of average of these would be in order. Well, that's kind of what Simpson's is. It's kind of an average. Now, what's that mean? Kind of an average. Well, it's actually what we call a weighted average. Simpson's is this. Simpson's is a weighted average. It's 2 midpoints plus a trapezoid divided by 3. Now, write down what I did here. Notice the 2n that I put here, and I'll talk about that in a minute. Okay, so just write that down. But a weighted average, we're going to take 2 midpoints plus a trapezoid and divide by 3. Here's why. Because it turns out that a midpoint is a little better than a trapezoid most of the time. Most of the time, a midpoint has about half as much error as a trapezoid. So let's say, and remember I said if one's over, the other one's under. So let's say the midpoint's off by 3. Then that means the trapezoid would be off by what? About 6. Well, if we're going to average those, and remember, one's under and one's over. So if the one that's under is off by 3 and the one that's over is off by 6, and we just do a simple average, what are we going to be? Over or under? If the midpoint is under by 3 and this one's over by 6, and we do a simple average, what's our answer going to be? It's going to be over, because more, right? Because more of our error is over. So what happens is, if this one's off by 3 and it's under, and this one's off by 6, it's over. How about we do 2 of these? If we do 2 of these that are off by 3, how much is that going to be off by? 6, right? I doubled the amount of error. This one that's under is off by 3. If I do 2 of those, it's off by 6. This one's off by 6, and then I average that. Then they're going to be close. You see what I mean? So that's a weighted average. So 2 of the midpoint plus a trapezoid, then divide by 3. Okay? That's why we do it that way. All right? So that's called a weighted average. Now, why is it 2 in there? Well, because when we divide up, this is why Simpson always has to be even. Here's what this means. Now, you're probably thinking, wait a minute, on the last screen we didn't do 2 in, right? No, that's true. If I'm doing an S6, I want this 6 to go right there. If I'm using this formula right here, okay, Simpson has 2 different formulas you can use, just like trapezoid. Trapezoid has this formula, and now we have this formula. So if I'm doing a T6, I want N to be 6. If I'm doing a T6, then I need an L6 plus an R6. Okay? But if I'm doing an S6, then I want to do an M3 and a T3 in my weighted average. Okay, so jot that down next to that formula you just wrote. Okay, that's why there's a 2N there. Remember, we said Simpson's is always even. So if I want to do a weighted average with an M3 and a T3, that gives me an S6. If I do an M4 and a T4, that gives me an S8. Right? If I do an M5 and a T5 and do a weighted average, that gives me an S10. That's why Simpson's is always going to be even. Now, how come it has to be that way? Well, if you look at your number line here, if I'm going to do an M3, let's say I had an integral that was going from here to here. I was going to do 6 subdivisions, right? Well, if I was doing a T3, here would be my subdivisions. Here, here, and here, right? So I'd have 3 subdivisions. But if I was doing midpoints, then I would be needing this point, and this point. Make sense? I got to use the ones in between. Well, if I'm going to add those together, I'm going to have heights at x2, x4, and x6, and I'm going to have heights at x1, x3, and x5. All of a sudden, I've ended up with twice as many subdivisions for Simpson. That's why Simpson's ends up always being even. Okay, if I'm adding up lefts and rights, those are the same subdivisions. X0, X1, the left and right share those same points. But trapezoid would be at X1, X4, X6, and the midpoints would be in between. If we're going to share those, if we're going to average those, we got to use them all. It doubles the number of subdivisions we end up with. Okay? So that's why it has to be that way. Okay, now let's take a look at what happens here. So this is the part you don't have to write down. So here I've written out an M3 for that number line up there. Makes sense? You see how X1's a midpoint, X3's a midpoint, X5's a midpoint? Makes sense? Okay? And then B minus A divided by 3, right? B minus A over N, right, is our subdivision. So B minus A over N, and I'm doing 3 of them, so it's B minus A over 3. Right? So that's a midpoint. The trapezoid would be, remember trapezoid's B minus A over 2N, right, from the other page. And my N is 3 because I'm doing a T3 here. Okay, so that gives me this. And then my trapezoid, remember I use the left edge, 2 of the next, 2 of the next, and then I use the last one. So X sub 0, 2 of these, 2 of these, and only 1 of those. Right? Okay, now I want to average those, but I want to do it with according to this formula here. So I want to take 2 of these, right? So now, what would happen if I took this times 2? Where could I put that 2? Now remember, it's kind of like I got this thing multiplied by this quantity and then multiplied by that thing. So it's kind of like having a 3 times a 4, and then in here I got like a 2 plus a 6 plus a 9, or I don't know, whatever. So could I distribute the 4 through there and not even mess and leave the 3 out here? Would that be okay?
Yeah.
Or I could take the 3 and distribute it through, or I could just take the 3 times the 4, right? So same thing here. I could take this 2 times this fraction, but I don't think that would help me any. It would just make it messier, actually. Or I could just take this 2 through these. You see what I'm saying? So because I'm trying to do this, I'm trying to take 2 times my midpoint. So I'm going to take 2 times this. So I'm just going to distribute this 2 into here. I'm going to leave this out here. You okay with that? Okay. So I'm going to take this 2 and I'm going to go through those. Okay. So now that gives me this. So my 2 M3s I've distributed, I got my 2's in there. Right? Now I want to add that to that. Okay, I'm just trying to do this right here. Trying to add 2 M3s plus a T3. Okay? So I want to add this to this. Now, when I add these together, problem is these aren't the same. Right? These don't look the same. And I need them to be, right? So when I add them together, I can pull that out. It's kind of like adding a, I need these to be the same. So how can I do that? Well, I get a common denominator. Right? So how can I get a common denominator here? Top and bottom times 2. So all I've done is multiply that by a 1, basically. Okay? Now this 2 times, I want this 2 to stay down here because I want this to match. But this 2 is just kind of in the way, right? So what can I do with this 2? Hint, like what we just did in the last screen. I could take this 2 and distribute it through there, right? And then my outside would just be b minus a over 2 times 3 like I have here, right? So now all of a sudden, what do I got in here? Now I got 4's in there, right? Now I got 4 of those, 4 of those, and 4 of those, right? So now I can add these together. So when I add these together, what am I have? I'm going to have b minus a over 6. And then what do I get when I add these together? I'll have 1 of those, 4 of those, 2 of those, 4 of those, 2 of those, 4 of those, and 1 of those, right? See what happened there? Okay, because I went in order, x sub 0, then x sub 1, x sub 2, x sub 3, x sub 4, x sub 5. Okay, and so we end up with that. Right? But, now that's just the top here, right? That's just the 2mn plus the tn. I haven't divided by 3 yet. Okay, so let's divide that by 3. So I got b minus a over 3. When you divide by 3, that just puts a 3 on the bottom, right? So now instead of just 6 on the bottom, it'd be 3 times 6. And look what I got. I got 6 subdivisions because it starts at x0, ends at x sub 6, right? So that's 6 subdivisions. Okay, it goes back to this screen here. 1, 2, 3, 4, 5, 6. 6 subdivisions. Okay, so that's my n, which is my n right there. So see how that's b minus a over 3n? Right? Remember back here on Simpson? B minus a over 3n. That's where that came from. And that's why it goes f of x0, then 4, then 2, then 4, then 2, like that. That's where it comes from. Okay? So it's just a bunch of algebra, taking 2 of these plus 1 of these and dividing by 3, and that's where this comes from. So now we got 2 rules we can use with Simpson. This one or this longer version. It's up to you. Now, when would you use this one for sure? If you were going to do an S8, how would you decide which of those you want to use? What did I tell you over here? If you're going to do a T6, when would you do this one for sure? If you already had L6 and R6, right? If you already had L6 and R6, then just average them and that gives you T6. But if you were starting from scratch and had to do T6, then you could, write out that one would be just about as fast. It's up to you. So when would you do this formula for sure if you want to do an S8? If you already had, if you want to do an S8, what do you have to have here? M, look down at my example here. If you had M4 and T4, then that little formula right there will give you S8. right? If you're starting from scratch and wanted an S8, you could just put 8 in for N and go that way, okay? Now, you need to see this because you're not getting it. So let's go. Let's do this problem right here. So we're going to write this down right here. So this is what this is going to look like. This is part of what you're going to be writing out on your homework today, okay? Now, in this chapter, capital I is used a lot. Stands for integral. That's our exact answer. That's our exact area, right? What we're studying here is approximations to integrals, approximations to areas, right? So I is our exact answer. All right, so here's a simple integral, 0 to 2, under the parabola x squared. So we're talking about this piece of area right here, right? We're doing an approximation of that. Okay? Now we can calculate that real easily. That's 1/3 x cubed from 0 to 2. Put a 2 in there, that would be 8/3 minus 0, which would be 8/3, right? So we know that that answer, and that's what, 2 2/3? 2.666 repeating is that area, right? So we know what the exact area is. Okay, let's do an L3 and let's just practice doing it according to the formulas we wrote down today. So I would start by writing what here? A top one right there. Right? So 2 minus 0 over 3 square bracket. Now here where it might be a good idea, on my x-axis we're going to divide this into 3 subintervals, right? So what are my widths here? 2/3, 4/3, and then of course 6/3. Now I don't care about actually using 6/3 because I'm not doing a sigma here. I'm not looking for a pattern, right? So how you write them is totally up to you. I'm gonna let you use your calculator to actually plug these in anyway, okay? But we're gonna write it out and then use our calculator to plug it in. So what's gonna go here? Now these are lefts. So it's gonna be f of 0 plus f of 2/3 plus f of 4/3. That's it. Now, let's go to our calculators and let me show you how you can help yourself make this a little quicker to go ahead and do this calculation. What I would do if I was doing this problem is I would define f of x to equal x squared. Okay? So I would say, oops. Okay, so I would go into my home screen here and I would go to menu or just type it, define f parentheses x equals x squared. Oops. Sorry. Yeah, thank you for catching that. Where's the equals? Okay, oh, there it is. Thank you. Okay, I would define f of x to equal x squared. So I'm not even going to, you do not have, when you write this out, you do not have to take it out of f notation, which is what we had been doing. So now you can just type in 2/3 times bracket f parentheses 0 plus f parentheses 2/3 plus f parentheses 4/3. Maybe hit Control Enter to get a decimal, or just hit Enter if you'd rather have that. 40/27. You agree with me on that? Does that look good? Okay. And so now I think decimals are better. So what was that? 1.481 Clearly, that's an under approximation. Correct? All right. Next one. 2 minus 0 over 3. What's going to be different here? F of 2/3 plus F of 4/3 plus F of 6/3 or just 2. Right? So I will want to, on our quiz next week, if I give you, this is where the rule will be. If it's less than 10, if it's single digits, we're going to write it out. I think the way we're writing it out now is a good way to write it. But if you wanted to do this the way we were doing it in chapter 5, if you want to go F of 0 times 2/3 plus F of 2/3 times 2/3 plus F of 4/3 times 2/3, if you don't go height times width, height times width, height times width, I'm fine with that. Not a problem. Okay, but I think it's good to practice it this way because sometimes you see this in multiple choice questions, you see it written this way, so I think it's good. Now on your calculator, you can save yourself a little bit. You can just arrow up, and the only thing we need is to replace the F of 0 with F of 2, right? And so that's that, or 4.148. 4.148, did I do that right? Clearly that is too much, but if you look at the picture, it's easy to see that yes, right rectangles are going to be over and lefts are going to be under. Okay, midpoint. It's a little more interesting here. Midpoint would be, again, 2 minus 0 over 3, b minus a over n. And then what's the first midpoint? No. 2, 6, which would be 1/3. So I'm just going to put 1/3, F of 1/3. I'm not worried about seeing a pattern here. Plus, what's the next one? Halfway between 2/3 and 4/3. That's 1, 3/3. Remember, we're going over 2/3, right? Our width here is 2/3. So if your first one's 1/3, next one will be 3/3, next one will be 5/3, right? But you got to be able to find those midpoints. So F of 5/3. And then on the calculator, and again, this only works because I've defined my function to be x squared. So it's plugging in for me here. And then what was it? 3/3. And then it was 5/3. So you can go in and just change a couple of numbers there. And look how accurate a midpoint is, even with only 3. 2.593. Is that what that rounded to? That's pretty darn accurate. Only 3 subdivisions. Only 3 subdivisions. Okay, now my T3. Now I'm going to do it, I don't know if I call it the longer way, but it would be right now, because what could I do right now to do a T3? I could average these, but I'm going to do the other one first, because I just want you to be able to, I just want some practice here doing both. So now what's a T3? It's 2 minus 0, b minus a, over 2 times 3. Right? 2n. And our n is 3 here because we're doing 3 trapezoids. Okay? And so what's a trapezoid? It starts at the left edge, so it'd be f of 0 plus 2 f of 2/3. Very good. You go to 2/3. We don't use the midpoint ones here in a trapezoid. Plus 2 f of 4/3 plus only 1 f of the right edge, which is 2. Now, I want you to notice something here. Look here now. On the left, notice how many heights you have in here. 3. And on the right, you have 3. And on the midpoint, you have 3. What do you got in the trapezoid? You always have one more, because you're using both the left and the right edge, correct? So you're always going to, if you're doing a T3, you should have 4 things inside of there. If you're doing a T8, you better have 9 things inside there. Okay, so when we go to add this one up, be very similar, except this is going to be a 6 down here. Okay, 2 times 3, and then this was a 0. I'm just kind of cheating here. And then this was a, what, 2/3? but there was 2 of those, right? And there was 2 of these, and that one was what, 4/3? I just didn't want to type all this again. And then plus 1 of the last one. 2.815. Now, notice that trapezoid midpoint were pretty close to the exact answer, weren't they? Which one's closer? Midpoint's a little closer. If you look at how much they were off, and one of the things we're going to talk about here today is we're going to talk about this right here. Now, we'll talk about this in a minute, but basically, isn't this just saying how much that L is off? Isn't this just, we'll write this down here in a minute, but isn't this just the amount of error? This is saying take the exact answer I minus your approximation. That's just the amount of error. Now, what do the bars do? Yeah, they're absolute value, but what does that do? Makes it positive. Why would we put that there? No.
In case it's over.
If it's over, if this is an over approximation, what would happen when you subtract here? You get a negative. If it's under, you'll get positive, right? Because this will be bigger, the exact answer. What we're saying is we don't really care if it's over or under. When we're figuring out how far are we off, we don't really care if we're over or under. So we just put bars around it to just make it positive, right? We don't want our error to be a negative number. We just want it to be positive because we don't really care. I mean, we're going to know if it's over or under, right? We just care about how much error there is. That's what the bars are doing there. Okay, back to this. So this one's a little bit more. And we can take this number minus that, and this number minus that, and see that this is a little closer than this one is. Okay, now, we could also have done what? To do a T3, you guys said we could do L3 plus R3 and divide by 2. So let's do that on our calculator real quick. Now I want to take unrounded values. So I'm going to come up here and I'm going to find my L3, which was this number, plus my R3, which was this number. I'm going to add those. I'm going to divide by 2. And sure enough, look what I get. 2.815. Exactly what we got when we did the trapezoid and wrote it out. Same thing. Okay, now let's practice our S6, because this is the one your eyes were all glazed over when I was doing it earlier. So the formula is B minus A over 3N. Now what is N on this one? What is N on this one? S6, what is N? 6. Go back to this formula. Go back to this formula down here. When we're doing an S6, the N is 6. That N is 6. When we're doing it out this way, that is 6. Only in this formula, right, was there the 2N there. Okay? All right. So S6, so N on this one is 6. So now what do we got? We got F of 0, the far left edge, plus 4F. Now don't say it. Everybody think about it. F of 0 plus 4F of, okay, now say it. No. 1/3. Remember, when we're doing Simpson, we're using not only those, but we're using the midpoints too, right? We're using the midpoints and the other ones. That's why we have 6 subdivisions. We're going to go here, to here, to here, to here, to there, to the end, right? We're using the midpoints also. So it's 4F of 1/3 plus 2F of 2/3 plus 4F of, all you have to do is go up to the midpoint and see what was the next midpoint. It was at 1 or 3/3. Maybe if you see the pattern, it's helpful here. Plus 2F of 4/3 plus 4F of 5/3 plus f of 2. And how many are in there? 7. One more, just like trapezoid, one more than the number of subdivisions. We had 6 subdivisions. There's 7 in there. Notice the 4-2-4 pattern. It automatically will end with the 4 like we want it to. Because if we're doing an even subdivision, since there's one more in there, there'll always be an odd number in there. It'll always work out perfectly, the 4-2-4 pattern. But notice the 4s. Remember, the 4s came on the midpoint ones. So the 4s are on the ones that are the midpoints. So the 1/3, the 3/3, the 5/3, those right there are the ones that end up with the 4s. Okay? All right. Now on our calculator, we can go do that, but I'm going to save the time real quick because the other option we had to do an S6 is what? 2 what? 2 M3s plus T3 divided by 3. That was our other formula for a S6. 2 M3s plus T3 divided by 3. So we can go to our calculator and we can go 2 times, where was our M? What was our M? It was 2.59, that one. Okay? 2 times that plus our T3, which was this one right here, 2.81. Hit enter. Divide by 3, and that is our S6. Oh my gosh. What is that? That is exact. Now, is that a coincidence? No, but it won't always be an exact. Here's the thing, and we're gonna finish this up here by talking about some over-under stuff. I tell you what, we'll come back to it after we do this next bit here. All right, so let's talk. This is the last thing we're going to talk about here. So, when is a left rectangle going to be over estimate? When the graph is what?
Concave up.
When will the left be over? When it's, I heard concave up and I heard decreasing. Which one? When it's decreasing. Concavity doesn't matter. When the function's decreasing, lefts are going to be over. When are they going to be under? When the graph's increasing. When will lefts be perfect? When the function is a horizontal line, lefts will be perfect. That's the only function that lefts will be perfect on. When will rights be over? The reverse, right? Oops. Sorry. Rights will be over when the function is increasing. And be under when the function is decreasing. It'll be, you don't have to memorize this, you can just picture it, just draw a picture, right? But they're the reverse. So when lefts are over, rights will be under, and that's why when we average them, we get a trapezoid, and that's why that's better. They're like partners. When will a trapezoid be over? Isn't that how you do a trapezoid? What causes that to be over? The concavity. When it's concave up, a trapezoid is going to be over. When it's concave down, it'll be under. Like this one. Right? What about a midpoint? Take a guess. Opposite. Now, we'll talk more about that tomorrow, but let me give you the quick version of it. In red here, let me draw a midpoint, rectangle. It'd be this guy right here, right? That would be a midpoint rectangle, correct? Yeah, that's not the best picture, you're right. Let me take this point and pivot it. Let me take that top of that rectangle and imagine that pivoting on that midpoint dot. You with me? If I were to pivot that, it would end up being a tangent to the curve right there. It would look like this. If I took that and I pivoted it, it would end up making what shape? A trapezoid. Wouldn't this area offset that area? Wouldn't that pivoted trapezoid be the same as the rectangle? And since it's tangent, isn't that going to be under the curve? So when a trapezoid is over, because of concavity, a midpoint's going to be under, because a midpoint rectangle can be thought of as a pivoted trapezoid. Okay? We'll look at that a little more closely tomorrow. But that's why we get what we get. And because of the curvature, is it easier to see why the midpoint's better? Do you see how this amount of error here is going to be less than this amount of error there? Because it curves into the midpoint pivoted trapezoid as opposed to curves away from the trapezoid, right? That's part of why midpoints are better. Okay. So, what kind of a function fits a midpoint or a trapezoid perfectly? Where would a trapezoid fit perfectly? What kind of function?
Straight line.
A line. Any diagonal line. So think about it. Left and right fit what perfectly? Horizontal. Not very common. Trapezoids and midpoints, and midpoint is a pivoted trapezoid, will fit lines perfectly. Right? Well, guess what? Simpson fits not only horizontal and lines perfectly, but it fits parabolas perfectly as well. And since the graph we just did was a parabola, we just did x squared, that's why Simpson actually gave us the exact answer. That was a cubic or a sine or something else that wouldn't fit perfectly. But parabolas are fit perfectly by Simpson's rule. Okay, it's kind of complicated why. We won't go into it, but it fits them perfectly. Okay, so for your homework. All right, and then there was this line. I said we get back to this, but there's really not much to say. On your homework, if it says find this, right? If on your homework it says find this, well, all you need is the exact area, which we did in this last problem. We found the exact area was 2.666 repeating. And then find L3, which we did, and then subtract it. It's just the amount of error. Find out how much each of those are off. So we can take each one of our answers here and subtract them from 2.666, and that's what that's asking. Okay? That's all that's saying. Okay? How much error is there? All right. You're going to have some questions at the beginning of the homework here where it's going to have you write out, like we did on this screen here, find L3, find R3, whatever. You can use your calculator to help you, just like we did here. But then a bunch of them at the end are going to be kind of some true-false kind of things. Or might be true, must be true, that kind of thing. And it has to do with the over-under stuff. So your homework pretty much exclusively has to do with this, writing this out, and this, the over-under. Okay? So an example, it would give you a function that is concave. Let me give you a function that's increasing and concave up. And then it would give you something like this. Is that always true, might be true, or must be true, might be true, or can't be true? So is a midpoint greater than a trapezoid on a function that's increasing and concave up? There's a trapezoid. Trapezoid is over, so what's a midpoint? Under, so can a midpoint be greater than a trapezoid on that function? No, so that would be, can't be true. Can't be true, that kind of thing. So it's asking you those kind of questions that have to do with over and under approximation. Okay, and I just draw myself little pictures, to be honest with you, when I want to think about the left, right, what's over, what's under. Okay, just draw little pictures and think about it. All right, that's your homework, the top line, 6.1, the first on this.